today they want us to talk about the lungs and the pressures that go into breathing. So the first pressure that we're going to look at is what's called the interpleural pressure. So the lungs have membranes that run right along the outside here of each lung, just like this. And they're like, this is the visceral pleural, and it's right along the edge of the lung. Didn't draw that super great, but it's right on the lung, the membrane of the lung. It's the visceral pleura. And then right out here along the chest cavity, if I can draw a relatively straight line, we have what's called parietal pleura. So visceral pleura, parietal pleura. And there's a little pressure in here that pulls these pleural membranes together. It's a negative pressure. It's about -3, -5 millimeters of mercury. And that is what's keeping the lung from collapsing. And why this is so important is because the lung, it comes down to the bronchi, into the alveoli. It's not anatomically correct, but just so you can see it. And these alveoli, they have elastin protein. The lungs actually everywhere. They have these elastin proteins everywhere. And those are constantly pulling the lung in to make it like want to collapse. But this negative pressure here is keeping that lung kind of suctioned out against the rib cage and the diaphragm and everything. And then from there, we also have other factors that make this lung want to collapse. So you have water molecules around the inside of each of these alveoli, right in there. And because of that, these have surface tension, or like the tension of water that wants to keep that surface together. You have surface tension in here. And that surface tension, if we were to look at like one alveoli is like a little circle. Draw this in blue and black. We have a little circle here, right? So that surface tension, if we were to draw this little, all that water there, that surface tension is constantly pulling the alveoli in, making it want to collapse. So, how do we stop the alveoli from collapsing? Well, inside the alveoli, we have these little molecules called surfactant, and they have a polar head, non-polar tail, and they kind of come in here, they interact, and they break up with the water. They interact with the water, and they break up that surface tension. So it relieves the tension. That takes us into Laplace's law. And so Laplace's law, we'll just go right here with this. Laplace's law. So this is pressure is equal to 2T over R. So if we have an alveoli, the R is for radius, R equals radius, T is surface tension, or just tension. But here it's for surface tension. It's just tension pulling it in. So if we have a smaller alveoli, this radius goes down, the pressure goes up. So in order to keep that pressure normalized, we have to have something to lower, or to lower that tension. So we have surfactant to lower that tension. In the larger alveoli, the radius is larger, or it's the same, but it's bigger. So we need less surfactant in those to kind of keep that tension the same, that pressure the same in there to make it not collapse. So now that we understand the pressures that are kind of pulling the lung in to make it want to collapse, how do we breathe? Well, down here, we have our diaphragm, and it sits up here with this parietal pleura and it helps create some of this negative pressure. When we want to breathe in, we know that air flows from an area of high pressure to low pressure. So if we want to breathe in, we need to create low pressure here. So what do? The muscles of the diaphragm contract, moving it down. As it moves down, it increases this negative pressure in the parietal space, the pleural space. And that pleural space that increases the pressure, or decreases it, I guess, makes it more negative, and thus making the pressure in here more negative, because we're emptying that space around the lung, and so air is going to flow in here. Air flows in and into the alveoli so that we can do gas exchange. And other things that contribute is we have our ribs out here. They will move out, moving that out with it, decreasing the pressure, and then your sternum out here in the front of everything, it'll also kind of rotate out to allow for more space, more negative pressure, better airflow in. And this actually brings us to pneumothorax, or a collapsed lung. So that happens when we no longer have this negative pressure here. So if we were to, say, get a hole in our lung right here, and then all the way out into the alveoli where the air comes in, the air would come in and then it would flow through and out into the pleural space, the pleural cavity. And in doing so, it would allow this to actually collapse, because this pressure would no longer be -3. It could get up to 1 or 2 or 5. It would be a positive pressure. And so it would start to collapse this lung, and that's what pneumothorax is. It is a collapsed lung. And this can happen from things like, sometimes this pleural space will get too close and it'll start creating friction, and that can actually tear the lung like this and allow air to come out. Or trauma to the lungs, like a gunshot wound could do this, getting stabbed, stuff like that. Anything that causes air to be able to flow in and allow that lung to collapse. And the case I talked about before, where that you can have rubbing and it can rip the lung, that can be really bad, because that just means that no air is also escaping out of that hole. Because if you have something that is all the way through the cavity, air can come in and out of that hole, and yes, the lung will collapse, but it won't just completely shrivel and close in on itself. But if there's nowhere else for that air to go, it will just continue to come in and just completely collapse that lung and not allow any air to move through it or out of it in any way. And that can actually build up in the entire chest cavity and cause a lot of problems. Okay, and then other things that impair respiration is loss of surfactant. I kind of talked about Laplace's law. If we have less surfactant, it's actually harder. There's more pressure in here, and so it's harder to move that to allow breathing. This becomes the higher the pressure. So higher pressure is equal to a more elastic lung. So it's harder to breathe air in because we don't have this surfactant breaking up that surface tension. And then the lower the pressure, if we have too much surfactant, that's a very compliant lung. And we have a hard time getting the air out, because this alveoli isn't going to want to collapse. It's going to be okay being stretched and open and dilated and stuff. So it's not going to want to push that air out. Okay. now that we've talked about the general anatomy and how breathing works, why is breathing necessary? So, in our bodies, we need gases. We need oxygen to survive. Our cells need oxygen, and we get that oxygen from the air. So I'm going to go over gas exchange now, and we're going to kind of simple this. So there's our alveoli, and here is our pulmonary artery coming in, and the pulmonary veins coming out of this gas exchange. So in this gas exchange, we have a very important equation, is the alveolar gas equation. The alveolar gas equation helps us determine the partial pressure of oxygen in the alveoli. So that is written as capital A, O2, okay, and that is equal to FiO2, or the partial pressure of oxygen in the atmosphere, that kind of thing, minus the atmospheric pressure, ATM, minus the pressure of H2O. And we're gonna take that, this is not minus, this is multiple that. So we erase this. So it's times atmospheric minus pressure of water. And then we're gonna subtract the P little a CO2 over R. And R is it's a constant. It's kind of like the oxygen, the CO2, the oxygen produced by the body by breaking down stuff. In a normal, healthy person, it's 0.8. So R is 0.8, 0.85. It's right in that area. So we'll put 0.85. So, why is this important? Because if we know the pressure of oxygen in here, we know how it's going to diffuse across that membrane there into the blood and be taken to the rest of the body. So if we have somebody who's having a lower PaO2, that can mean that their lung isn't functioning properly. They're not getting the oxygen they need. An example of this is for, perfectly healthy individual, perfectly healthy lung. We have 0.21 for the FiO2 because it's about 21% of the air oxygen, times the atmospheric pressure. And atmospheric pressure at sea level is about 760. 760 minus the pressure H2O, which is a constant, it's 50, minus 40 over 0.85. And that comes out to a PaO2 of about 101. 100, 101, it's somewhere in there. This is for a normal, healthy individual. So that means as oxygen comes in, we have the regular partial pressure of oxygen in the atmosphere, which is up in the 180s, 190s, it's up there. But when we get down into here, I'll represent this with little green dots. We have our O2, and then the partial pressure of oxygen in the alveoli, so the PaO2, is about 101. What does that mean? So as blood flows in and flows out, we're going to have different partial pressures of oxygen and carbon dioxide and everything. And so we'll start with that. CO2 in the stuff leading up to the alveoli. We call that PV CO2, or all the partial pressures in the veins in this case. But this is an artery, but it's in the veins leading up to the arteries and stuff. So our PVCO2 is about 45 millimeters of mercury. And then the So that's here in that artery. And then we have the P CO2, the PA CO2, P big A CO2 in the alveoli is about 40. So this carbon dioxide, it has a tendency, I'll draw that in blue dots, to move into the alveoli and eventually out into the lungs and atmosphere. We breathe it out. Oxygen, as it's coming in, we'll put a couple here, its PVO2 is equal to about 40 millimeters of mercury. Now that's a big difference, 40 to the 101 here. So what happens is as the blood comes by, this will diffuse down into the blood until, as it's leaving, the P little a O2 is equal to 101 millimeters of mercury. So the partial pressure of oxygen in the arteries is equal to 101 millimeters of mercury. So how do we do that? Because there are different laws of gases and stuff, and carbon dioxide is much more readily dissolved in water than oxygen is. So a lot of the oxygen is actually not carried directly in the blood. We need a transporter for that. So here is our transporter. I'm gonna erase this real quick, and I'm gonna draw, let's just go right over here. I'll draw it bigger. I'm gonna draw a red blood cell. Erase that a little bit. Okay, so we have a red blood cell here. Inside this red blood cell, we have what is called hemoglobin. I'll just put HB, and I'll put 4 of them. But in reality, there are millions of hemoglobins in the body. They're in the blood cell. In each blood cell, there are tons of hemoglobin. So what happens is as the blood is coming through here and into there, a lot of magic happens right here in this red blood cell. In the red blood cell, we have different molecules of heme and everything on these hemoglobin. There are 4 chains. Each chain can carry 1 oxygen on a heme center, a heme with an iron center. And so we can have 4 O2s per hemoglobin. And that would be a completely saturated hemoglobin. So what happens is these, I'll draw a little red blood cell in the vein here, just to kind of show you kind of how this works. Oxygen would come in to the blood. Right there, we have an oxygen. And it's not very well soluble in the blood. So what it'll do is the red blood cell actually pick it up and bind it on a hemoglobin. So that's what happens here. We have an O2 here, it'll come in there and bind. And that takes it from the blood in where it's not very well dissolved into a red blood cell where it can bind to these hemes and be in the blood still, but not dissolved. And when that happens, this is now out of the blood and another one can come in to create this partial pressure of oxygen. So it's just replacing everything. One comes in, it gets taken in, another one replaces it, and it gets taken until this is completely saturated and it can keep going down to the tissues. And because of that, there are like certain percentages of carriers. There are still some free floating oxygens in the blood. That's about 2% of all the oxygen transported in the body. And then this here, that's 98% carried in the body. So what happens when we get down to a tissue and we need to exchange gas? When we get down to a tissue and we need to get rid of this oxygen, I'll put a tissue cell right, erase that, make my point. Maybe put a tissue cell right here. That's a tissue cell. So we have oxygen just free floating out in the blood, right? O2, and this needs oxygen. So this O2 come down into the tissue cell, leaving a space behind it in the blood, which in turn allows this to come out into the blood and leave the hemoglobin. And it's just the opposite of what happens at the alveoli. Instead of an oxygen coming into the blood then going to the hemoglobin, the tissue cell is in need of oxygen, and so it pulls an oxygen from the blood, and then the blood will pull an oxygen from hemoglobin and out. And the way this happens is down in these areas, these cells are creating CO2. So they're creating CO2, they're letting it out into the blood, and then these CO2s, they need to be transported. And the percentages of CO2 as they're transported is a little different because CO2 is a little more dissolvable in blood. So what happens is the CO2 will come out, some of it's dissolved in the blood. This is a smaller percentage. It's about 7%. You have about 7% of just free CO2s in the blood. Other ones will come up here, they'll go into the cell, and they can actually bind to hemoglobin as well. Different binding site, they can bind to hemoglobin as well. So we have a CO2 up here on the hemoglobin. The CO2 on the hemoglobin, that is roughly 23-ish%. So 23% of the CO2. And then here's the big one. Inside of the red blood cell, we have the enzyme carbonic anhydrase, so CA. So what happens is we'll bring in another CO2 there. And obviously there's water, H2O, it'll come in. And what we create is bicarbonate, HCO3 and H+. That hydrogen will come over and it'll bind to a hemoglobin, because hemoglobins can actually absorb hydrogens. They're pretty decent at monitoring the acids and bases inside of the red blood cell. And then here on the side of the red blood cell, let's put a dot there, we have a transporter. And this transporter will take bicarbonate, put it out of the cell into the blood, so HCO3 in the blood, and it'll take a chloride, so Cl-, and it'll put it into the red blood cell, antiport style. And this is called a chloride shift, and it's the way that we keep the same kind of negatives in the red blood cell. We keep that charge. So what happens? Gas exchange back at the lungs as far as CO2 goes. So we have the free floating stuff that just readily diffuses across the membrane and is breathed out. As we get back to where gas exchange needs to happen, same thing, as one of these goes out, some from a red blood cell, I'll draw a new red blood cell over here, do another red blood cell here, CO2 from those hemoglobins will come out and replace it. And it continues to do that, just cycle through that. And we also have that carbonic anhydrase in here, right? Carbonic anhydrase, which can take bicarbonate, HCO3, pull it in exchange for a chloride, Cl- comes out. That'll come in, and then the hydrogen come off of the hemoglobin, and it'll create CO2 and water. And that CO2 will also come out of the red blood cell and be diffused across and everything. And yeah. So that is the transport of gases and how they are exchanged at the cellular level as well as the alveolar level, percentages, and this equation. And why that matters is if we have somebody who, for some reason, is not getting the right amount of oxygen, say that their percentage of oxygen that they're getting goes down to like 19%, so this is 0.19. You'd see how this would go down, and change that would also go down. We'd get less oxygen. The hemoglobin would get less saturated because there's not as much pressure. We wouldn't get as much oxygen to the tissues. It creates a whole systemic kind of chain of events, which now we'll talk about hemoglobin dissociation curves, saturation and dissociation curves, and how those apply to us. So we have a curve that tells us about hemoglobin and pressures of oxygen and how they're related. So here we have PO2, so pressure of oxygen, and here we have percent sat, or percent saturation, okay? So this curve up here is obviously 100, and PO2, we have like 100, 101 right over there, like where we usually are. We have a little curve that kind of looks like that, and right in here at 40, this is where our like tissue cells, that's where they are. That's where their pressure of O2 is. So what happens is when we're at 100, do this in green right here, we can see that if we follow that up and we follow this over, they roughly meet. They're supposed to. So let me redraw this curve a little bit. It's gonna go like that, okay? So they meet roughly at 100 and 100, it roughly meets. Not perfectly, because we know that 101 is where we usually are, and you can never really get the hemoglobin 100% saturated. We shoot for 98%, because that's a good number. Because as you go down, you don't really get much change in this curve until you get to somewhere around 50, 40, and it starts really dropping. Because that is where we'll start unloading oxygen out of the hemoglobin into the tissue cells. So at about 40, that's where you'll really see this, 40, that's where you'll really see this curve take that dip and go down. And that's at about 75% saturated. You know, they're about 75% saturated. So below 40, it's going to start dumping oxygen out and into the cells, and we'll get down lower. But there are things that will change how this is. So we have what's called a right shift and a left shift. A right shift would make this look something like that, and a left shift makes it look something like that. So there's a lot of things, there's a few things that can control the shift. And so we have hydrogen ions, something called 2,3-bisphosphoglycerates, but I'm just going to put BPG, temperature, and the last one, pH temp. The last one is CO2. Okay, so things that will cause this right shift, or what we call a T state in the hemoglobin, a state where it won't bind as much, it won't bind to as many oxygens, is an increase in protons, so the pH goes down. We have an increase there, increase in temp, and a decrease or increase in CO2. Increase in CO2. So what happens is as hemoglobin sees more hydrogens and it has to bind to them, its affinity for oxygen goes down. It goes into a T state, it doesn't bind to as much oxygen. This 2,3-BPG, it actually binds to hemoglobins, causing a T state, meaning less oxygen. Increased temp causes a T state, less oxygen, and CO2, as it binds, it decreases the affinity for oxygen. So, as these go up, we're gonna see this right shift, which means for every pressure of oxygen, we are getting less saturated. More pressure, less saturation, less oxygen binding. And then the exact opposite is true for this left shift. We see decrease in hydrogens, a decrease in 2,3-BPG, a decrease in temp, and a decrease in CO2. We're going to be able to bind more oxygen to hemoglobins, get it more saturated at a lower partial pressure of oxygen. And this is important because if we need to get oxygen to the tissues, we're going to need to do something to unload that oxygen. We can increase these to unload that oxygen at the tissue level. In fact, that's kind of what happens at the tissues. Muscle cells and stuff, as they're working, they increase their temp. They increase CO2 as a byproduct. And even hydrogens as a byproduct sometimes. Those are bind to the hemoglobin and dump off that oxygen. And then when we're trying to get things done, back, the oxygen back on, opposite happens. And then this 2,3-BPG, this is only made in two places, our red blood cells and placentas. So that is the hemoglobin dissociation and curve, factors that affect it, and I think that's it.